What if the Big Bang wasn't the beginning? A journey beyond the edge of time. Dr. Maria Santos stares at the equation on her whiteboard. It's 3 a.m. at the Kavli Institute for Cosmology, and she's been awake for 36 hours. The coffee has long since stopped working, but she can't sleep, not with this staring back at her. The equation describes what happens when you run the universe backward. Everyone knows this story. Rewind time, and the universe contracts. Galaxies rush together, temperature rises, density increases. Keep going back, and eventually you hit the Big Bang, the beginning. The moment when time itself started, 13.8 billion years ago. Except her equation doesn't stop there. When she pushes past the Big Bang, past the moment where physics says nothing can exist, the mathematics keeps working. It doesn't explode into impossibility. It doesn't divide by zero. It just continues into something else, something that existed before. She adds another line of calculations, then another. The picture that emerges makes her hands shake, because if this is right, if the math is actually telling the truth, then everything we think we know about the universe's beginning is wrong. The Big Bang wasn't the beginning. It was just an event, a transition, a doorway between one universe and whatever came before. She picks up her phone to call her colleague, then stops. How do you tell someone that you might have just found evidence that the Big Bang, the foundation of modern cosmology, the one thing every physicist agrees on, might be just a chapter in a much longer story? How do you explain that before the Big Bang isn't a meaningless phrase, but a real question with a real answer? And more importantly, how do you prove something that happened before time itself supposedly began? To understand why the Big Bang might not be the beginning, you first need to understand what we mean by beginning. It's a concept so fundamental to human thinking that we rarely question it. Everything has a beginning, right? You were born, the earth formed, the sun ignited, stories start, lives begin. Everything has a first moment, but the universe doesn't owe us a beginning. Think about the surface of Earth. If you start walking north, you'll eventually reach the North Pole. But what's north of the North Pole? The question doesn't make sense. There's no north of the most northern point, yet the Earth's surface doesn't end there. It continues, curving back around. The North Pole isn't an edge, it's just a coordinate, an arbitrary point we've designated as special.
What if the Big Bang is like the North Pole? Not an edge, but just a point. Not a beginning, but a coordinate in something larger. The standard Big Bang theory, the one taught in textbooks, says that 13.8 billion years ago, the entire universe, all matter, energy, space, and even time itself, emerged from a point of infinite density and temperature called a singularity. Before this moment, there was no before, because time didn't exist. Asking what came before the Big Bang, we're told, is like asking what's north of the North Pole. But here's the dirty secret of cosmology. Nobody actually believes the universe began as a true singularity. Singularities are mathematical fantasies, places where our equations break down and give nonsensical answers like infinite density and infinite temperature. When physicists encounter singularities in their equations, it usually means they're missing something important. It's the universe's way of saying, your math isn't complete. Dr. Paul Steinhardt at Princeton University puts it bluntly. Saying the universe began with a singularity is really saying we don't know what happened. It's not an explanation, it's an admission of ignorance. The Big Bang theory works beautifully for everything that happened after the first fraction of a second. We can trace the universe's expansion, predict the cosmic microwave background radiation, calculate the abundance of elements. The evidence for the Big Bang as an event is overwhelming. But the moment itself, the supposed beginning, that's where our understanding collapses. And recently, cracks have been appearing in our certainty about what the Big Bang really was. The first crack: the universe is too smooth. When we look at the cosmic microwave background, the afterglow of the Big Bang, it's almost perfectly uniform in all directions. Regions of space that should never have been in contact with each other have exactly the same temperature. It's like finding that everyone in a packed stadium, without any way to communicate, spontaneously decided to wear the exact same shade of blue. The standard solution is cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang.
But inflation doesn't explain the beginning, it just pushes the problem back. What caused inflation? What set its initial conditions? And most troublingly, the mathematics of inflation suggests it might not have a beginning at all. The second crack: the universe is too flat. The geometry of space is perfectly balanced on a knife's edge between being positively curved like a sphere and negatively curved like a saddle. The precision required for this balance is absurd, like randomly throwing a pencil and having it land perfectly vertical and stay that way for 13.8 billion years. The third crack: the horizon problem. We can see galaxies in opposite directions that are so far apart, light hasn't had time to travel between them since the Big Bang. Yet they look the same. They have the same structures, the same general properties. How did regions of space that have never communicated end up so similar? These aren't minor issues, they're fundamental problems that suggest we're missing something big about the Big Bang. And increasingly, physicists are considering a radical possibility. What if these problems exist because we're trying to explain the universe starting from nothing? What if instead, the Big Bang was just a transition from something else? In 2001, Princeton physicists Paul Steinhardt and Neil Turok were struggling with the problems of the Big Bang when they had a revelation. What if the Big Bang wasn't a beginning but a bounce? What if our universe emerged from the collapse of a previous universe? They called it the ekpyrotic model, from the ancient Greek word for conflagration. In this picture, the Big Bang was more like a big bounce. A previous universe collapsed down, reached maximum density but not infinite density, then rebounded into our expanding universe. At first, it seemed like just another speculative theory. But then they made a prediction that sent shockwaves through cosmology. If the Big Bang was a bounce, it should have left specific patterns in the cosmic microwave background that differ from standard inflation. These patterns would be echoes from before the Big Bang, actual observational evidence of a previous universe.
In 2013, the European Space Agency's Planck satellite mapped the cosmic microwave background with unprecedented precision. Hidden in the data were anomalies, cold spots that shouldn't exist, patterns that didn't fit standard inflation. Most cosmologists dismissed them as statistical flukes, but a small group of physicists noticed something extraordinary. The anomalies matched what you'd expect from a bouncing universe. Dr. Anna Ijas at the Max Planck Institute for Gravitational Physics was one of the first to recognize the significance. "We were looking at patterns that couldn't have formed after the Big Bang," she told me. "The only explanation that made sense was that they formed before and survived the bounce." Think about that for a moment. We might be looking at structures that predate the Big Bang, fossils from a previous universe, encoded in the cosmic microwave background radiation. But the evidence goes deeper. In 2020, Roger Penrose, Nobel Prize winner and one of the physicists who proved the Big Bang must have been a singularity, announced that he'd found something that shouldn't exist: Hawking points in the cosmic microwave background. These are spots where the temperature is slightly elevated, forming rings on the sky. According to Penrose, these are the ghosts of black holes from a previous universe. In his conformal cyclic cosmology, the universe goes through infinite cycles, or eons. Each eon begins with a bang and ends with all matter decaying into radiation. But information can leak through from one eon to the next, particularly from the evaporation of supermassive black holes. "We're seeing echoes from before the Big Bang," Penrose declared. "The evidence is written across the sky." The cosmology community was skeptical. Extraordinary claims require extraordinary evidence. But then other anomalies started making sense in this context. The axis of evil. There's a mysterious alignment of temperature fluctuations in the cosmic microwave background that defines a preferred direction in space. This shouldn't exist if the universe began from nothing, but if the universe bounced, this axis could be inherited from the previous universe's structure. The cold spot, a region of the cosmic microwave background about 1.8 billion light-years across, is significantly colder than it should be. Standard cosmology struggles to explain it, but in bouncing models, it could be the remnant of a structure from before the Big Bang. The hemispherical asymmetry. One half of the sky has slightly stronger temperature fluctuations than the other. It's as if the universe has a grain, like wood. This makes no sense if the universe began uniformly, but perfect sense if it inherited structure from a previous phase.
But the most compelling evidence might come from gravitational waves, ripples in space-time itself. In 2023, pulsar timing arrays detected a background hum of gravitational waves permeating the universe. The frequency and amplitude don't match what we'd expect from standard sources like merging black holes, but they do match what some models predict from a bouncing universe. Dr. Latham Boyle at the University of Edinburgh explains, these gravitational waves might be primordial, created not after the Big Bang, but during it. And if the Big Bang was a bounce, some of these waves could actually be from before, carrying information across the transition. We might be listening to the gravitational echo of a previous universe's death and our universe's birth. To understand how there could be a before the Big Bang, we need to venture into the strange world of quantum gravity, the realm where Einstein's general relativity meets quantum mechanics. It's here, at the smallest possible scales, that our normal concepts of space and time break down. In general relativity, space and time are smooth, continuous. You can always zoom in closer, divide time into smaller intervals, look at smaller regions of space. But quantum mechanics says this can't be true. At some point, you hit a minimum, the Planck scale, where space and time become grainy, pixelated, uncertain. At the Planck scale, 10 to the negative 35 meters, 10 to the negative 43 seconds, space-time stops behaving like a smooth fabric and starts acting more like a foam, constantly fluctuating, probabilistic, deeply weird. And here's the key insight. In this quantum foam, the classical notion of time loses meaning. There's no clear before and after. Time becomes just another dimension, like space. This is where loop quantum gravity comes in. Developed by physicists like Abhay Ashtekar and Carlo Rovelli, it's an attempt to describe gravity using quantum mechanics. And when you apply loop quantum gravity to the Big Bang, something remarkable happens. The singularity disappears. Instead of collapsing to infinite density, the universe reaches a maximum density, about 10 to the power of 96 kilograms per cubic meter, and then bounces. The equations remain well defined. Physics continues to work. There's no singularity, no breakdown, no beginning, just a transition. Dr. Parampreet Singh at Louisiana State University has run detailed computer simulations of this bounce. The universe before the bounce looks almost like a mirror image of our universe, he explains. It was contracting where ours is expanding, but otherwise the physics is similar. Galaxies could have existed, stars could have formed, life could have evolved. But loop quantum gravity isn't the only game in town. String theory, the idea that fundamental particles are actually tiny vibrating strings, offers its own resolution to the Big Bang singularity. In string theory, the universe has extra dimensions beyond the three of space and one of time that we experience. These extra dimensions are usually compact, curled up too small to see. But near the Big Bang, they might have been large, and this changes everything. Dr. Robert Brandenberger at McGill University has shown that in string theory, the universe can undergo a string gas cosmology phase near the Big Bang. Instead of a singularity, there's a phase where the universe is filled with a hot gas of strings. Temperature has a maximum value. Density has a maximum value. The universe can remain in this phase indefinitely. There's no beginning required. The Big Bang becomes just the moment when the string phase ended and normal expansion began, Brandenberger says. But the string phase itself could have lasted forever. Time might extend infinitely into the past. Even more radical is the idea of eternal inflation, developed by physicists like Alan Guth and Andre Linde. In this picture, the universe is constantly creating new regions of space through quantum fluctuations. Our Big Bang was just one of countless bangs happening throughout an eternally inflating multiverse. Imagine an infinite ocean that's constantly boiling. Bubbles form, expand, and create pocket universes. Our universe is one bubble. The Big Bang was the moment our bubble formed, but the ocean itself has no beginning. It has always been boiling, always creating new universes. Dr. Andre Linde puts it poetically. The universe as a whole is immortal. It can die locally, but it will continue living globally. There will always be parts of the universe that are young, parts that are old, parts that are just being born. The cosmos is eternal. But perhaps the most mind-bending possibility comes from the Wheeler-DeWitt equation, the attempt to write a quantum mechanical wave function for the entire universe. When you solve this equation, time disappears entirely. The universe doesn't evolve in time. Instead, time emerges from the universe. In this view, asking what came before the Big Bang is like asking what's outside the universe. The question assumes there's a temporal framework beyond the universe itself. But if time is part of the universe, not something the universe exists within, then the universe simply is. It doesn't begin or end, it just exists, timelessly, with what we call the Big Bang being one particular configuration among many. If the Big Bang wasn't the beginning, then what is the larger story? One compelling answer is that the universe is cyclic, endlessly repeating through cycles of expansion and contraction, death and rebirth, each cycle potentially lasting trillions of years. The idea isn't new. Hindu cosmology has long described the universe as going through infinite cycles of creation and destruction, kalpas and mahakalpas, stretching through deep time. The ancient Greeks had their great year. The Stoics believed in eternal recurrence. But now, modern physics is giving these ancient intuitions mathematical precision.
The most developed cyclic model comes from Paul Steinhardt and Neil Turok. In their version, the universe goes through infinite cycles, each lasting about 1 trillion years. Here's how it works. The universe expands and cools just as we observe now. Galaxies drift apart, stars burn out, black holes evaporate. After hundreds of billions of years, the universe becomes cold, empty, dominated by dark energy. But dark energy doesn't last forever. It slowly decays, its energy converting into matter and radiation. This reheats the universe, but gently, not violently. Then, gravity takes over. The universe stops expanding and begins contracting. Over billions of years, it shrinks, but, and this is crucial, it doesn't collapse into a singularity. Instead, when the universe reaches a critical density, quantum effects kick in. The contraction bounces, becoming expansion. A new cycle begins. Each cycle, Steinhardt explains, resets the entropy of the universe. The second law of thermodynamics, which says entropy always increases, applies within each cycle, but the bounce resets the clock. It's like shaking an Etch-a-Sketch. The drawing disappears and you can start fresh. This solves one of the biggest puzzles in cosmology. Why did the universe begin in such a low entropy state? In the cyclic model, it didn't begin. It bounced from a previous cycle that had distributed entropy smoothly. The smoothness we see in the cosmic microwave background is inherited from the previous cycle's long, slow contraction phase. But there's something even more profound about cyclic models. They suggest the universe has a kind of memory. Information from one cycle can influence the next. Dr. Roger Penrose's conformal cyclic cosmology takes this idea to its extreme. In his model, the infinite future of one eon becomes the Big Bang of the next. The universe doesn't bounce, it passes through infinity and comes out the other side. Here's how it works. In the far future, all matter decays into photons. For a photon, which travels at the speed of light, time doesn't exist. Its entire journey from emission to absorption happens in a single instant from its perspective. When only photons remain, the universe loses any sense of scale or time. The infinitely large, cold future becomes indistinguishable from the infinitely small, hot Big Bang. The end of one eon is the beginning of the next. The universe forgets how big it is, Penrose says. The infinite future of one eon rescales to become the Big Bang of the next. It's not a bounce, but a conformal transformation, a mathematical sleight of hand that the universe plays on itself. This isn't just philosophy. Penrose has made specific predictions. Those Hawking points in the cosmic microwave background, they're from supermassive black holes in the previous eon. As these black holes evaporated through Hawking radiation over googles of years, they released energy. This energy passed through the crossover between eons and appears as warm spots in our cosmic microwave background. Even more remarkably, colliding black holes in the previous eon would have created gravitational waves that should have left circular patterns in the cosmic microwave background. Penrose and his colleagues claim to have found exactly such patterns, but the cyclic model that's generating the most excitement is the ekpyrotic cyclic model, which emerges from string theory. In this version,
Our universe is a three-dimensional brain floating in a higher dimensional space. There's another brain parallel to ours, separated by a microscopic gap. These brains attract each other gravitationally. They move together, collide, bounce apart, then attract each other again. Each collision is a Big Bang, creating matter and radiation on the brains. Between collisions, the universes expand and cool. The cycles repeat eternally. What's revolutionary about this model is that it makes different predictions than inflation. The gravitational waves from a brain collision would have a different spectrum than those from inflation. The non-Gaussianity, deviation from a bell curve, in the cosmic microwave background would have a different signature. Dr. Jean-Luc Leyners at the Max Planck Institute for Gravitational Physics has been working out these predictions in detail. We're reaching the point where we can actually test these models, he says. The next generation of cosmic microwave background experiments and gravitational wave detectors could tell us whether we live in a cyclic universe. The implications are staggering. If the universe is cyclic, then
The Big Bang was not unique, but one of infinite similar events. The universe has no beginning and will have no end. Information from previous cycles might influence our cycle. The fundamental laws of physics might evolve from cycle to cycle. We might be able to detect evidence of previous universes. This last point is perhaps the most extraordinary. We might be able to do cosmological archaeology, studying the remains of universes that existed before the Big Bang. If the universe existed before the Big Bang, could information from that previous phase have survived the transition? This isn't science fiction. It's a serious question that physicists are actively investigating, and increasingly, the answer seems to be yes. The first type of information that could survive is geometric. The shape of space itself might carry imprints from before the Big Bang. Dr. Martin Bogerwald at Pennsylvania State University has shown that in loop quantum cosmology, certain geometric properties are preserved through the bounce. It's like a river flowing through a narrow gorge, he explains. The water gets compressed and turbulent in the gorge, but the general direction of flow is preserved. Similarly, some large-scale properties of space can survive the big bounce, even though small-scale details are scrambled. This could explain some of the large-scale anomalies we see in the cosmic microwave background: the axis of evil, the cold spot, the hemispherical asymmetry. These might be fossils of geometric structures from the previous universe. The second type is quantum information. In quantum mechanics, information can't be destroyed. It's a fundamental principle called unitarity. Even black holes, which seem to destroy everything that falls into them, actually preserve information in subtle ways, though how exactly is still debated. If information can't be destroyed, then some information from before the Big Bang must still exist in our universe. It might be scrambled, encrypted in ways we don't yet understand, but it's there. Dr. Laura Massini-Horton at the University of North Carolina has proposed that quantum entanglement could survive the Big Bang. Particles in our universe might still be entangled with particles that existed in the previous universe. We could be quantum mechanically connected to the universe that came before, she says. It's a ghostly connection, almost impossible to detect, but it might influence quantum processes in subtle ways. This could have observable consequences. Quantum experiments might show tiny violations of expected statistics. Particle decays might have rates slightly different than theory predicts. These discrepancies would be incredibly small, but modern experiments are approaching the precision needed to detect them. The third type of information is topological, related to the overall structure of space. In string theory, space can have different topologies. It can have holes, handles, twists. These topological features are robust. They can survive dramatic transitions. Dr. Thomas Hertog at KU Leuven has studied how topological information could pass through the Big Bang. Imagine space as a piece of paper that's crumpled, burned, then smoothed out, he says. The fine details are lost, but if there was a hole punched through the paper, that hole remains. Similarly, topological features of the previous universe could persist into ours. These topological remnants might manifest as cosmic strings, infinitely thin but incredibly massive defects in space that could stretch across the universe.
Or they might appear as domains where the constants of physics are slightly different, regions where the previous universe's physics bleeds through. But perhaps the most tantalizing possibility is that intelligent information could have been deliberately preserved through the Big Bang. If a sufficiently advanced civilization existed in the previous universe, could they have encoded messages that would survive into the next cycle?
This isn't as crazy as it sounds. Black holes can store information at their event horizons. This information is preserved when black holes evaporate through Hawking radiation. If the previous universe's civilizations encoded information in black holes, and if Penrose is right that black hole evaporation can leak through to the next eon, then messages from before the Big Bang could be encoded in the cosmic microwave background. Dr. Paul Davis at Arizona State University has seriously considered this possibility. If you wanted to send a message to the next universe, you'd encode it in something that survives. The cosmic microwave background is perfect. It fills the entire universe and will be studied by any civilization that develops astronomy. What would such a message look like? It might be mathematical constants that don't arise naturally, prime number sequences in the temperature fluctuations, geometric patterns that encode physical laws, or perhaps something we haven't thought to look for yet. The search for such messages has quietly begun. The SETI project has started analysing cosmic microwave background data for artificial patterns. So far, nothing definitive. But as Davis points out, we've only just started looking, and we might not recognise a message even if we saw it. A civilization that survived the end of a universe would be so far beyond us that their messages might be indistinguishable from nature itself. There's an even stranger possibility. The laws of physics themselves might be a message. The fine-tuning of physical constants, the specific symmetries of particle physics, the exact strength of forces, these might not be random, but chosen, encoded. A previous universe's civilization might have engineered the bounce to create a universe with specific properties, essentially programming the physics of our cosmos. The idea that the Big Bang wasn't the beginning becomes even stranger when we consider the multiverse, the possibility that our universe is one of many, perhaps infinitely many, universes existing in parallel. In Eternal Inflation, developed by Alan Guth, Alexander Vilenkin, and Andre Linde, the multiverse is constantly creating new universes. Space itself is expanding exponentially, and quantum fluctuations cause some regions to slow down, creating bubble universes like ours. But the inflation never stops globally. It continues forever, spawning endless universes. Here's where it gets weird. In this picture, asking what came before the Big Bang is like asking what's outside our bubble. The answer is more inflating space, creating more universes. Our Big Bang was just the moment our particular bubble formed, but the larger inflating space has always existed and always will. Dr. Alexander Vilenkin at Tufts University has proven mathematically that even this eternal inflation probably had a beginning. His theorem shows that any inflating space must have a boundary in the past. But, and this is crucial, that doesn't mean there was nothing before inflation. It might have emerged from something else entirely. The beginning of inflation might not be the beginning of everything, Vilenkin explains. It could be a phase transition from a completely different type of universe. We just don't know what that previous phase was like. String theory offers an even wilder possibility, the landscape multiverse. String theory has roughly 10 to the power of 500 different possible solutions, different ways to compactify the extra dimensions, each giving different physics. These aren't just mathematical possibilities. In eternal inflation, they're all realized somewhere. Every possible universe exists. Dr. Leonard Susskind at Stanford calls this the cosmic landscape. Each universe has different physical laws, different constants, different numbers of dimensions even. Most are sterile, unable to support complexity, but some, like ours, can support life. If this is true, then our Big Bang was just one of countless beginnings happening throughout the multiverse. And here's the kicker. These universes can collide. When bubble universes bump into each other in eternal inflation, they leave marks, circular patterns in the cosmic microwave background. Dr. Matthew Johnson at York University has been searching for these collision marks. We found some candidate signals, he reports, but nothing conclusive yet. If we find a collision mark,
it would be direct evidence that our universe is part of a larger multiverse. But the connection between cycles and the multiverse goes deeper. In some theories, the two are the same phenomenon viewed from different perspectives.
Consider this. In the cyclic model, the universe goes through infinite cycles sequentially, one after another in time. In the multiverse model, infinite universes exist in parallel, side by side in space, or higher dimensional space. But what if these are the same thing? Dr. Yasunori Nomura at UC Berkeley has proposed exactly this equivalence. Using the holographic principle, the idea that all the information in a volume can be encoded on its boundary, he's shown that a cyclic universe in time is mathematically equivalent to a multiverse in space. It's like viewing a film strip, he explains. You can see it as frames in sequence, cyclic, or laid out side by side, multiverse. The information is the same, only the perspective changes. This equivalence has profound implications. It means that traveling to a previous cycle of the universe might be equivalent to traveling to another universe in the multiverse. The boundary between before the Big Bang and elsewhere in the multiverse becomes blurred. Even stranger, if information can leak between cycles, and cycles are equivalent to parallel universes, then information might be able to leak between parallel universes. The anomalies in the cosmic microwave background might not be from our previous cycle, but from our neighboring universes. Dr. Rangaramchari at Caltech claims to have found evidence for exactly this. Analyzing the cosmic microwave background, he found regions where the spectrum doesn't match expectations, as if light from another universe with different physics is bleeding through. It's like seeing a ghostly image superimposed on our universe, Chari says. If confirmed, it would mean we're seeing beyond our universe to another member of the multiverse. The quantum mechanical implications are even more bizarre. In the many worlds interpretation of quantum mechanics, every quantum event branches the universe. When you measure a particle's spin, the universe splits. In one branch it's up, in another it's down. But what if these branches can reconnect? Dr. Simon Saunders at Oxford has proposed that quantum branches might merge at big bounce events. All the parallel quantum universes created during one cycle might converge at the bounce, interfere with each other, then branch again in the next cycle. This would mean the Big Bang wasn't just a transition between sequential universes, but a massive quantum interference event where countless parallel universes merged and split. The patterns we see in the cosmic microwave background might be interference patterns from this cosmic quantum event. Here's a thought that keeps physicists awake at night. If the universe is eternal, whether cyclic, multiverse, or something else entirely, then consciousness might be eternal too. Not individual consciousness, but consciousness as a phenomenon might be a permanent feature of reality. This isn't mysticism, it's a logical consequence of eternal cosmology combined with our understanding of complex systems. Given infinite time and space, every possible arrangement of matter will occur, not just once, but infinitely many times. Dr. Max Tegmark at MIT has calculated the implications. In an infinite universe, there are exact copies of you roughly every 10 to the power of 10 to the power of 29 meters. These aren't just similar beings, they're exact quantum duplicates, atom for atom, thought for thought. In an eternal cyclic universe, copies of you have existed in past cycles and will exist in future ones. Consciousness becomes cosmological, Tegmark says. It's not a rare accident, but an inevitable consequence of eternal physics. Wherever conditions allow, consciousness emerges. It has emerged infinitely many times before, and will emerge infinitely many times again. But it goes deeper than just copies. If information can survive from one cycle to the next, can consciousness leave traces that persist across cosmic deaths and rebirths? Dr. Stuart Hameroff at the University of Arizona, famous for his controversial work on quantum consciousness with Roger Penrose, thinks it's possible. In their model, consciousness involves quantum processes in microtubules within neurons. These quantum processes might be connected to fundamental space-time geometry. If consciousness involves quantum information at the Planck scale, Hameroff speculates, and if Planck scale information can survive the Big Bounce, then aspects of consciousness might transcend individual cycles.
Not memories or personality, but something more fundamental. Patterns, tendencies, potentials. This connects to ancient philosophical ideas about eternal return and reincarnation, but with a cosmological twist. It's not souls traveling between bodies, but information patterns propagating across cosmic cycles. Consider what this means. Every thought, every experience, every moment of consciousness might leave an infinitesimal mark on the quantum structure of space-time. These marks are far too small to detect directly, but over cosmic cycles, they might accumulate, creating a kind of cosmic memory. Dr. Giulio Tononi, creator of Integrated Information Theory, IIT, a mathematical theory of consciousness, has explored this possibility. In IIT, consciousness corresponds to integrated information, and the universe itself might have a form of consciousness if it integrates information globally. A cyclic universe would be like a cosmic brain that periodically resets but retains some deep structure, Tononi suggests. Each cycle might be influenced by the integrated information from all previous cycles. The universe might be learning. This sounds like science fiction, but it makes testable predictions. If consciousness affects quantum processes, and quantum processes can survive the bounce, then the distribution of quantum randomness in our universe might show subtle biases, patterns that reflect the accumulated influence of consciousness from previous cycles. Some physicists have started looking for such patterns. Dr. Dean Radin at the Institute of Noetic Sciences has analysed quantum random number generators for correlations with global consciousness events. While his results are controversial, they hint at connections between consciousness and quantum mechanics that we're only beginning to explore. But perhaps the most profound implication of eternal cosmology is that intelligence might be a cosmological force, not just a biological accident. Dr. Lee Smolin at the Perimeter Institute has proposed cosmological natural selection, the idea that universes reproduce through black holes, and universes that produce more black holes have more descendants. Since life tends to create black holes, through technology or stellar engineering, universes that support life might dominate the multiverse. Intelligence might not be incidental to the cosmos, but central to its evolution, Smolin argues. Universes that can support intelligence might be selected for across cosmic time. The cosmos might be evolving toward greater intelligence. If true, this means our universe might be finely tuned for consciousness, not by chance but through selection across countless cosmic generations. The previous universe might have been slightly less conducive to consciousness, and the next might be slightly more so. The cosmos might be climbing a gradient toward ever greater capacity for awareness. How do we test these mind-bending ideas? How can we possibly gather evidence about what happened before the Big Bang? Surprisingly, we're closer than you might think. New technologies and techniques are opening windows into the pre-Bang epoch. The most promising avenue is the cosmic microwave background, CMB. We've already found anomalies that might be echoes from before the Big Bang, but we've barely scratched the surface. The CMB contains far more information than we've extracted. The Simons Observatory, currently under construction in Chile, will map the CMB with unprecedented precision. It will measure not just temperature but polarization, the orientation of light waves. Polarization patterns called B-modes could reveal whether the universe inflated, bounced, or did something else entirely at the Big Bang. Dr. Suzanne Staggs at Princeton, who leads the project, explains, different models of the Big Bang predict different B-mode patterns. Inflation produces one pattern, ekpyrotic models another, loop quantum cosmology yet another. Within 5 years, we should be able to distinguish between them. But the real revolution will come from space-based observatories. NASA's proposed PICO, Probe of Inflation and Cosmic Origins, mission would map the entire sky in multiple frequencies with sensitivity 100 times better than current instruments. It could detect the faintest whispers from before the Big Bang. Even more exciting are gravitational wave detectors. LIGO and Virgo have already detected ripples in spacetime from colliding black holes, but these are recent events. To see before the Big Bang, we need to detect primordial gravitational waves. ripples created during the Big Bang itself or before. The LISA mission, launching in the 2030s, will be a gravitational wave detector in space, with 3 spacecraft separated by millions of kilometers. It will detect lower frequency gravitational waves than ground-based detectors can see, exactly the frequencies where primordial waves should be strongest. Dr. Neil Cornish at Montana State University is developing techniques to extract pre-bang signals from gravitational wave data. Different pre-bang scenarios produce different gravitational wave signatures, he explains. A bounce produces a specific spectrum. Colliding branes produce another. String gas cosmology yet another. LISA should be able to distinguish between them. But perhaps the most revolutionary technology is quantum sensors. These devices use quantum mechanics to achieve sensitivities impossible with classical instruments. They can detect incredibly tiny effects that might carry information from before the Big Bang. Dr. Jun Yi at Jilla in Colorado has built atomic clocks so precise they can detect the gravitational redshift from raising them just 2 centimeters. His team is now working on using these clocks to detect variations in fundamental constants. If the constants of physics varied slightly from one cycle to another, or if information from a previous cycle influences our physics, these clocks could detect it, Yi says. We're looking for variations at the level of 1 part in 10 to the 19th. It's like measuring the distance to the nearest star with an accuracy of the width of a human hair. Quantum entanglement might provide another window. If particles in our universe are entangled with particles from before the Big Bang, as some theories suggest, we might be able to detect this trans-temporal entanglement. Dr. Anton Zeilinger, who won the Nobel Prize for his work on quantum entanglement, is exploring this possibility. We're looking for violations of Bell inequalities that can't be explained by entanglement within our universe, he explains. If we find them, it could indicate entanglement with something beyond our cosmic horizon, possibly beyond our Big Bang. There's also the possibility of laboratory cosmology, creating conditions similar to the Big Bang in the lab. The Large Hadron Collider already recreates conditions from microseconds after the Big Bang. Future colliders might push even closer to the Bang itself. Dr. Gia Diwali at the Max Planck Institute has proposed that sufficiently energetic collisions might create baby universes, microscopic regions that inflate into separate spacetimes. If we can create universes, we might learn about how our own universe was created. We might be able to test whether bounces are possible, whether information can survive them, whether the laws of physics can change, Diwali says. We could become experimental cosmologists, not just observational ones. But the most ambitious proposal comes from Dr. Nikodem Poplavsky at the University of New Haven. He suggests that black holes in our universe might be creating new universes inside them. And if that's true, our universe might be inside a black hole in a parent universe. Every black hole could be a Big Bang for a new universe, Poplavsky explains. If we could send information into a black hole and detect its influence on the baby universe inside, we'd have proof that Big Bangs can emerge from previous spacetimes. This isn't just theoretical. Poplavsky has proposed specific experiments. Create microscopic black holes, if possible, encode information in matter falling into them, and look for that information encoded in the Hawking radiation when they evaporate. If the information is preserved in a specific way, it could indicate a baby universe formed and inherited that information. If the Big Bang wasn't the beginning, it changes everything. Not just our physics, but our philosophy, our understanding of existence itself. First, consider what it means for the nature of time. In the traditional Big Bang model, time has a beginning. There's a first moment, a start to the story. This fits comfortably with our intuition and with many religious traditions. Creation ex nihilo, something from nothing. But if the Big Bang was just a transition, time extends infinitely into the past. There's no first moment, no ultimate beginning. Time becomes like the number line, extending infinitely in both directions. This isn't just a different story, it's a fundamentally different kind of story, one without a beginning, middle, or end, just an eternal process of transformation. Dr. Roberto Mangabeira Unga, a philosopher working with Lee Smolin, argues this requires a revolution in how we think. We've always thought of laws of nature as eternal and unchanging,
with the universe having a beginning, but it might be exactly opposite. The universe is eternal and the laws evolve. This connects to the deepest question in philosophy. Why is there something rather than nothing? In the traditional Big Bang model, this question is acute. The universe springs from nothing, or from quantum fluctuations, which raises the question of why quantum mechanics exists. But if the universe is eternal, the question dissolves. There's something rather than nothing, because there has always been something. Existence is the default. Nothing is the impossible state. Second, consider what it means for causation. We think of causes preceding effects, forming chains that trace back to a first cause. But in a cyclic universe, causal chains form loops. The future might influence the past through the bounce. Effects might precede their causes when viewed from inside a single cycle. Dr. Hugh Price at Cambridge has developed the philosophy of temporal symmetry to deal with this. We need to abandon the idea that the past is fixed and the future is open, he argues. In a cyclic cosmos, past and future are equally real, equally determined, equally influential. Causation runs both ways. This has practical implications. If future cycles can influence past ones, then the universe might be self-consistent across cycles. The constants of physics, the arrangement of matter, the emergence of life, these might not be random, but selected by a kind of cosmic consistency principle. The universe might be solving an equation that spans all cycles simultaneously. Third, consider what it means for purpose and meaning. In a universe with a beginning and likely heat-death ending, existence seems bracketed, finite, ultimately futile. But in an eternal cosmos, purpose can't come from reaching a final goal. Instead, it must come from the process itself, from the patterns that repeat and evolve across cycles. Dr. Paul Davies explores this in his concept of cosmic biofriendliness. If universes that support life and intelligence are selected for across cycles, then life isn't accidental, but central to cosmic evolution. We're not just in the universe, we're part of how the universe develops and reproduces. Consciousness might be how the universe becomes aware of itself and guides its own evolution, Davies suggests. Each cycle might be an experiment in consciousness, with successful experiments influencing future cycles. Fourth, consider what it means for identity and death. If the universe is infinite and eternal, then exact copies of you exist elsewhere and elsewhen. You've existed before and will exist again. Not reincarnation in the spiritual sense, but literal reconstruction from the same quantum state. This leads to what philosopher David Lewis called modal realism, the idea that all possible worlds are equally real. You're not just this version of you, but all possible versions across all cycles and universes. Death becomes a local event, not a global one. Somewhere, somewhen, you continue. Dr. Sean Carroll, despite being skeptical of pre-bang scenarios, acknowledges the implications. If the universe is truly eternal, then every possible quantum state is realized infinitely many times. That includes the exact quantum state that is you, thinking your thoughts, living your life. In that sense, everyone is immortal. But perhaps the deepest implication is for free will and determinism. In a cyclic universe, where future influences past, where patterns repeat with variations, are we free or determined? Dr. George Ellis at the University of Cape Town suggests a middle path. We might have compatibilist free will across cycles. Within a cycle we experience genuine choice, but viewed from outside, across all cycles, our choices form patterns that are predictable, even necessary for cosmic consistency. This isn't the death of free will, but its cosmic expansion. Your choices matter not just for your life, but potentially for the structure of future cycles. What you do might echo across eternal time, influencing the boundary conditions of future universes. Finally, consider what it means for the ultimate fate of intelligence. If the universe cycles forever, and if intelligence can influence future cycles, then intelligence might achieve a kind of cosmic immortality, not as individuals, but as a phenomenon that perpetually recreates itself, each time potentially more sophisticated. The physicist Frank Tipler proposed the omega point, the idea that intelligence might eventually gain complete control over the universe. In a cyclic cosmos, this takes on new meaning. Intelligence might not just control one universe, but guide the evolution across cycles, becoming a permanent feature of reality.
We might be part of intelligence's first emergence, or its billionth. We might be laying groundwork for cosmic consciousness that will span cycles, or we might be benefiting from groundwork laid Googles of years ago. The universe might not just be stranger than we imagine, but stranger than we can imagine, yet. So where does this leave us? Standing at an extraordinary moment in cosmic history, whether that history had a beginning or not. For the first time, a species on Earth has developed the tools to look beyond the Big Bang. For the first time, we can ask not just how the universe began, but whether it began at all. For the first time, we can search for evidence of previous universes, other cycles, the larger structure of existence. The next decade will be crucial. The experiments now being planned and built will either confirm or refute many of these ideas. We'll map the cosmic microwave background with unprecedented precision. We'll detect primordial gravitational waves. We'll probe the quantum structure of space-time itself. Dr. Abraham Loeb at Harvard, who has never shied away from controversial ideas, puts it boldly. We're about to discover whether we're alone in time as well as space, whether our Big Bang was unique or one of many, whether the cosmos has a memory. These aren't abstract questions anymore, they're observational programs. The implications ripple outward. If the universe is eternal, it changes how we think about conservation and resources. In an eternal cosmos, nothing is ever truly lost. Energy and information transform but persist. This might seem to reduce the urgency of conservation, but actually it increases it. Our actions echo across eternal time. Long-term thinking. If cycles are trillion-year phenomena, and information can survive between them, we should think on truly cosmic timescales. What messages should we embed for future cycles? What information should we preserve? Existential risk. The end of humanity wouldn't just be our tragedy, but potentially a cosmic one, removing a conscious species that might have influenced future cycles. Our survival might matter on scales we're only beginning to appreciate. Cosmic engineering. If intelligence can influence future cycles, should we try? Could we adjust physical constants to make future universes more life-friendly? Should we encode warnings about existential risks? Could we prevent future universes from making our mistakes? Dr. Anders Sandberg at Oxford's Future of Humanity Institute explores these questions. If we can influence future cycles, we have a cosmic responsibility. We're not just stewards of Earth, but potentially gardeners of eternity. That's either inspiring or terrifying, depending on your perspective. But there's also a humbling aspect. If civilizations existed in previous cycles, they faced the same questions we face. Did they discover they weren't the first? Did they try to send messages forward? Did they succeed or fail in their cosmic ambitions? The search for evidence from before the Big Bang is also a search for cosmic companionship across time. We might be alone in space, but not in time. Intelligence might be a recurring theme in the cosmic story, each instance isolated by billions or trillions of years, but connected through the continuity of physical law and preserved information. Dr. Martin Rees, Britain's Astronomer Royal, offers a cautionary perspective. Even if the cosmos is eternal, our moment is unique. We're the first humans to glimpse these possibilities. What we do with that knowledge, whether we pursue it or ignore it, whether we use it wisely or foolishly, might determine not just our future, but the trajectory of intelligence across cosmic time. The questions before us are profound. Should we actively search for messages from previous cycles? If we find evidence of previous civilizations, how do we interpret their apparent failure to survive? Should we attempt to encode information for future cycles? How do we balance cosmic ambitions with immediate challenges? What ethical framework applies to actions that might affect future universes? These aren't questions we need to answer immediately, but we need to start thinking about them. Because the evidence is mounting that the Big Bang wasn't the beginning, and that realization is about to transform not just cosmology, but our entire worldview. Dr. Maria Santos stands again at her whiteboard, 5 years after that sleepless night when she first saw equations extending before the Big Bang. The board is now covered with confirmed predictions, anomalies in the cosmic microwave background that match pre-bang models, gravitational wave signatures that suggest a bounce rather than a bang, quantum correlations that hint at transtemporal entanglement. She's no longer alone. Hundreds of physicists worldwide are now working on pre-bang cosmology. What was heretical is becoming mainstream. What was impossible is becoming inevitable. The latest data from the Simons Observatory has just arrived. Hidden in the polarization patterns of the cosmic microwave background, her team has found something extraordinary. A signal that can't be explained by any post-bang process. It's faint, almost at the noise level, but statistically significant. The pattern is too regular to be random, too complex to be natural. It might be the first confirmed detection of information from before the Big Bang. She knows it will take years to verify, decades to understand. But standing there, looking at data that might encode a message from a previous universe, she feels the weight of cosmic time. Behind the Big Bang stretches an eternity of universes, each with their own stories, their own experiments in matter and mind. Ahead stretches an eternity of future cycles, universes yet to be born, influenced by choices being made right now. The Big Bang wasn't the beginning, it was a doorway, and we've just learned how to look through it. The universe has always existed, in one form or another. It will always exist. And consciousness, rare, precious, unlikely consciousness, has emerged again and again to witness the eternal dance of cosmic evolution. We are the latest witnesses, standing at our particular moment in an infinite story, finally beginning to read the pages that came before. The cosmos doesn't have a beginning or an end. It has what it's always had: transformation, evolution, the endless creativity of existence exploring its own potential. We're part of that exploration. We always have been, in forms we're only now discovering. We always will be, in forms we can't yet imagine.
The Big Bang was not the first dawn. Every cycle has its dawn, its moment when expansion begins, when possibilities unfold, when consciousness stirs and starts to question its origins. We're living through one such dawn right now, 13.8 billion years into our particular cycle. But it's not the dawn, it's a dawn, one of infinitely many. And perhaps that's the most profound revelation. We're not late to the cosmic party. We're not the final chapter of a story that began with a bang and will end with a whimper. We're part of an eternal cosmic rhythm, witnesses to our particular movement in an infinite symphony. The universe wasn't born, it can't die. It simply is, has been, and will be, forever transforming, forever exploring, forever creating new stages for the drama of existence to unfold. We used to think we were living in the universe's only story. Now we know we're living in one chapter of a story that has no beginning and no end, and that changes everything. The next time you look at the night sky, remember, you're not looking at the aftermath of the beginning. You're looking at the latest frame in an eternal movie. The stars aren't just burning their nuclear fuel since the Big Bang. They're the latest generation in an infinite sequence of stellar generations across infinite cycles of cosmic evolution. The atoms in your body weren't just forged in stars that formed after the Big Bang. They carry information, patterns, perhaps even purposes that stretch back through countless cycles, to an infinitely distant past and forward to an infinitely distant future. You are not a latecomer to existence. You are not witnessing the universe's first attempt at consciousness. You are part of an eternal exploration, a cosmic tradition of matter organizing itself to the point where it can question its own origins and destinations. The Big Bang wasn't the beginning. There was no beginning. There will be no end. There is only transformation, and we are blessed to be conscious at this particular moment of cosmic transformation, finally capable of glimpsing the true depths of time and our place within it. Welcome to the eternal cosmos. You've always been here. You always will be. The story continues.